49 years ago, a machine slightly larger than a small car lifted off from a launch pad in Florida, carrying a mission so modest on paper that nobody involved in building it expected it to still be running today. It was supposed to fly past 2 planets, take some pictures, and go quiet within 5 years. Instead, it kept going. It left the planets behind. It left the sun's own protective bubble behind. It became the first object built by human hands to physically cross into the space between the stars. And it kept talking to us the entire way, sending back a signal that, even now, takes over 22 hours to arrive. It's still talking today, in 2026, older than almost every person who currently works on its mission team, carrying a message intended for whoever or whatever might find it drifting through the dark long after everyone who built it is gone. This is the story of Voyager 1, the farthest machine humanity has ever built, and everything it has found since the moment it left home. To understand how a 5-year mission turned into the longest, farthest-reaching journey any human-made object has ever taken, you have to start at the very beginning, with a launch nobody expected to matter this much, decades later. Voyager 1 launched on September 5, 1977 from Kennedy Space Center in Florida. Its assignment, as originally conceived, was almost humble by comparison to what eventually happened. Fly past Jupiter, fly past Saturn, take photographs, gather measurements, and then fade quietly into retirement sometime around 1981. NASA's engineers at the time were focused on far more immediate concerns: the swirling storms of Jupiter's atmosphere, the intricate structure of Saturn's rings, the basic mechanics of getting a spacecraft safely past 2 of the largest planets in the solar system using cameras and instruments built with 1970s technology. Nobody on that original team was seriously planning for a spacecraft that would still be sending data home nearly half a century later, from a region of space no human instrument had ever reached before. Voyager 1 reached Jupiter in March of 1979, sending back the first close, detailed images of that planet's swirling storms and its 4 largest moons, discovering active volcanoes on the moon, Io, in the process. The first time anyone had ever observed volcanic activity on a world beyond Earth itself. It reached Saturn in November of 1980, capturing extraordinary images of the planet's rings and its hazy, orange-tinted moon, Titan. By the time it finished with Saturn, Voyager 1 had completed everything its original mission had asked of it. What happened next set the entire remaining trajectory, both literal and figurative, of the spacecraft's future. Rather than sending Voyager 1 onward through the plane of the solar system toward the other outer planets, the way its twin, Voyager 2, would eventually go on to visit Uranus and Neptune, mission planners used a close pass by Saturn's moon Titan to bend Voyager 1's path sharply upward, out of the flat plane where all the planets orbit, and send it climbing away from the solar system entirely. It was a deliberate trade-off. Voyager 1 gave up any chance of visiting another planet in exchange for a closer look at Titan's thick, hazy atmosphere, which scientists suspected correctly might hold clues about the kind of chemistry present on early Earth. From that point forward, Voyager 1's course was set. It was leaving, and it was never coming back. Voyager 1 used the gravity of Jupiter and Saturn the way a slingshot uses tension, picking up speed with every pass, and it simply never stopped moving. By the late 1980s, it had already become the most distant human-made object ever launched into space, a title it has held ever since. Before its cameras were permanently switched off, in February of 1990, Voyager 1 completed one final assignment, one that almost never happened at all. Astronomer Carl Sagan had spent years advocating for an unconventional idea. Before the spacecraft's imaging system was shut down for good to conserve power for the long journey ahead, turn the cameras around and take one last photograph, not of anything new, but of the place Voyager 1 had come from. Mission engineers were initially cautious, since pointing the camera back toward the inner solar system meant pointing it dangerously close to the sun itself, risking damage to the delicate optics. Sagan kept pushing, and on February 14, 1990, from a distance of roughly 7 billion miles, Voyager 1 executed a sequence of 60 images capturing as many of the solar system's planets as possible in a single coordinated sweep. A project that became known as the Solar System Family Portrait. In the frame containing Earth, our entire planet appears as a single point of light, less than a pixel across, caught almost by accident inside a stray beam of scattered sunlight. Sagan later described that image in a 1994 commencement address at Cornell University as showing Earth as nothing more than a mote of dust suspended in a sunbeam, and pointed out that every human being who had ever lived, every war fought, every king and peasant, every triumph and tragedy in the entire span of human history had played out entirely on that single, nearly invisible point of light. That photograph, known ever since as the pale blue dot, remains, to this day, the last image Voyager 1's cameras ever captured. They have not taken a picture since. With its imaging system retired, Voyager 1 continued outward using its remaining instruments, and in August of 2012, 35 years after launch, it reached a milestone no spacecraft had ever reached before. It crossed the heliopause, the boundary marking the true edge of our solar system. Here's how to picture that boundary. The The sun doesn't just provide heat and light, it continuously releases a stream of charged particles called the solar wind, which blows outward in every direction, pushing against the surrounding space and forming a vast protective bubble around our entire solar system, a bubble that contains every planet, moon, asteroid, and spacecraft we've ever launched. The outer edge of that bubble, the point where the solar wind finally loses its strength against the pressure of the interstellar medium pressing in from the other side, is the heliopause. Everything inside it belongs, in a very real sense, to our solar system. Everything outside it belongs to something else entirely. When Voyager 1 crossed that boundary in 2012, it became the first human-made object in history to physically leave the solar system, not as a metaphor or a technicality, but as a literal, physical fact, and it kept transmitting from the far side. What Voyager 1 found once it crossed that line is where this story becomes genuinely remarkable, because almost none of it matched what decades of careful, peer-reviewed scientific modeling had predicted. For decades before Voyager 1 ever reached the heliopause, physicists had built detailed models describing what interstellar space should look like. Relatively calm, thin, cold, and largely undisturbed, a quiet transitional zone between our solar system and the vast emptiness separating it from the next star. Starting in 2017, Voyager 1's plasma wave instrument began detecting something that didn't fit that quiet picture at all. A persistent narrowband signal, a kind of steady hum embedded in the plasma of interstellar space, showed up not as a single, brief blip, but continuously year after year, tracked across a stretch of interstellar space more than 900 million miles wide, roughly 10 times the distance between the Earth and the Sun. Researchers studying that data, publishing their findings in the journal Nature Astronomy, described interstellar space as turbulent and structured in ways earlier models had never predicted. Not empty, not quiet. Active, with a physical texture that had remained completely invisible to us because no instrument had ever been sitting inside that environment before to detect it directly. That signal remains, even now, only partially explained. Scientists have narrowed the possible causes down to two specific mechanisms: ordinary thermally excited plasma oscillation, the natural vibration of charged particles interacting with their surroundings, or something called quasi-thermal noise, a distinct physical process that would require real revisions to existing models of the interstellar medium if it turns out to be the correct explanation. Telling these two possibilities apart requires either more data from Voyager 1 itself, increasingly difficult to gather as more of its instruments are shut down to conserve power, or an entirely new mission specifically built to study interstellar space, one that doesn't currently exist and isn't currently funded. If such a mission were designed and launched starting today, researchers estimate it wouldn't reach the heliopause for at least another 25 years. Whatever the true answer turns out to be, Voyager 1's own data may remain the closest thing scientists have to a direct answer for a very long time. Voyager 1 also found something strange about the boundary itself at the exact moment of crossing. Instruments on the spacecraft, and later confirmed by its twin Voyager 2, recorded plasma temperatures right at the heliopause somewhere between 30,000 and 50,000 Kelvin, comparable to conditions found near the surface of certain stars. Some science writers have taken to calling this region informally a wall of fire, though the honest explanation requires care rather than taking that nickname at face value. There's no combustion happening out there, nothing burning in any conventional sense. Temperature, in physics, measures how fast individual particles are moving, not how much heat those particles can transfer to something sitting among them. Because the region is so extraordinarily sparse, with particles spread thin across billions of miles of space, there simply aren't enough of them colliding with anything to transfer meaningful heat. Voyager 1 passed directly through a measured plasma temperature that would vaporize almost anything on Earth. In its 1970s-era electronics didn't register so much as a change in operating temperature, because there was nearly nothing there to physically touch it. A third finding involved magnetism, and it touched on a genuinely fundamental question about how separated our solar system actually is from the rest of the galaxy. Before Voyager 1 reached the heliopause, the standard prediction was that the magnetic field environment on either side of the boundary should differ sharply. The Sun's own field on the inside, an entirely separate galactic field on the outside, expected to diverge clearly right at the crossing point. Voyager 1's magnetometer recorded something different. The magnetic field just beyond the boundary pointed in almost the same direction as the field inside it. With only one data point, researchers couldn't be certain whether that reflected something genuinely real about the boundary, or was simply a coincidence tied to Voyager 1's specific location. When Voyager 2 crossed the same kind of boundary 6 years later in 2018, from a completely different position on the opposite side of the solar system, its own magnetometer recorded the same alignment. NASA's own science communications team described this directly, confirming that what had initially looked like a surprising, possibly coincidental result from Voyager 1 turned out to be a genuine pattern. Our solar system, it turns out, isn't as magnetically sealed off from the wider galaxy as earlier models had assumed, a finding that still doesn't have a fully settled theoretical explanation. None of these discoveries came easily, and in 2023, Voyager 1 came close to losing the ability to tell us about any of them ever again. For 5 months that year, the spacecraft continued transmitting a signal, but what it sent back was corrupted, unreadable, scrambled data that engineers at NASA's Jet Propulsion Laboratory, after decades of experience reading everything the spacecraft had ever sent, simply could not decode. The cause, once identified, turned out to be a single memory chip inside the spacecraft's flight data system that had physically degraded after nearly 5 decades of exposure to cosmic radiation. There was no possibility of a repair mission. The component was over 15 billion miles away, and even a radio signal moving at the speed of light took about 22 hours to reach the spacecraft, with another 22 hours required for any response to come back. Every diagnostic step in the recovery effort took a minimum of about 44 hours to complete, and everyone carried the risk that a single incorrect instruction sent across that distance could end the mission permanently, with no chance of recovery. The team at JPL worked through that problem for months, methodically, under a level of pressure most engineering situations never produce. They eventually determined the corrupted code couldn't be repaired in place, but it could be relocated, split into smaller sections, and rewritten to function correctly from new locations in the spacecraft's available memory, then carefully reconnected to work as a whole again. By April of 2024, Voyager 1 was transmitting clean, complete, readable scientific data once more, and what it immediately resumed sending was more of that same persistent, unexplained plasma signal, more evidence of the same structured turbulence in interstellar space that nobody had fully explained before the spacecraft went quiet, and nobody has fully explained since. That resilience matters enormously for understanding what's happening to Voyager 1 right now in 2026, because the same aging power supply that nearly ended the mission through hardware failure is now ending it more gradually, through simple, unavoidable physics. Voyager 1 runs on a radioisotope thermoelectric generator, a sealed device that converts the heat produced by decaying plutonium into electricity. At launch, it produced roughly 470 watts. Nearly 49 years later, it produces a small fraction of that, and loses about 4 watts of capacity every single year permanently, with no possibility of refueling or replacement. On February 27, 2026, during a routine, planned calibration roll, a standard maneuver the mission team has executed many times over the decades, Voyager 1's power levels dropped further than engineers expected. Rather than risk letting the spacecraft's automatic safety systems handle the situation on their own, a process that would have meant an uncertain recovery stretched across a communication delay of more than 23 hours in each direction, the team at JPL made a deliberate, difficult decision. On April 17, 2026, they sent the command to permanently shut down the low-energy charged particles instrument, a device that had operated almost continuously since Voyager 1's launch in 1977, nearly 49 uninterrupted years of service. Of the 10 identical sets of instruments the spacecraft originally launched with, 7 have now been permanently retired. But the team hasn't given up on buying more time. Engineers at JPL are currently testing an experimental power restructuring procedure, nicknamed internally the Big Bang, designed to recover small amounts of electrical capacity currently being lost to inefficiency in the spacecraft's aging systems. Because any change to hardware this old carries genuine risk, the team chose to test the procedure first on Voyager 1's twin, Voyager 2, which currently has a slightly larger power margin, making a failed attempt there less costly to the overall mission. Those tests were scheduled for May and June of 2026. If they succeed, the same fix will be attempted on Voyager 1 itself no earlier than July. And according to NASA's own published statement on the plan, if it works, there is even a chance that Voyager 1's shutdown instrument could be switched back on. There's also a specific, already confirmed milestone sitting on the calendar, one that will arrive regardless of how that repair attempt goes. According to NASA's own tracking data, on November 18, 2026, at 2:16 a.m. Pacific time, Voyager 1 will reach a distance of exactly 1 light day from Earth, roughly 16 billion miles, meaning a radio signal traveling at the speed of light will take a full 24 hours just to reach the spacecraft, and another 24 for a reply to come back. Send a command on a Monday morning, and you won't know it was received until Tuesday, and you won't hear anything back until Wednesday. No human-made object has ever operated at that distance while still transmitting. It's worth pausing on what that actually feels like for the people running this mission day to day. Every test of a fix, every diagnostic check, costs nearly 2 full days round trip before anyone knows if it worked. Imagine trying to solve a problem in a house you can only visit for a few seconds every other day. Through a mirror where the instructions you send take a full day to arrive, and another full day to confirm whether they worked. That's the operating reality at JPL right now, for a machine that can't be visited, can't be manually rebooted, and can't absorb a single wrong move. Voyager 1 keeps moving regardless of any of this, about 38,000 miles farther out every hour, with nothing in interstellar space to slow it down. No atmosphere, no meaningful friction, nothing strong enough to meaningfully pull it off course. NASA's own projections put the end of its transmissions sometime in the early 2030s, when its remaining power finally falls below what's needed to run anything at all. But the spacecraft itself doesn't stop. In roughly 300 years, it will reach the inner edge of the Oort cloud, the vast shell of icy debris marking the outer limit of the sun's gravitational reach. It won't finish crossing that cloud for another 30,000 years after that. Attached to its frame is the Golden Record, a gold-plated copper disc carrying greetings recorded in 55 human languages, the sounds of rain and ocean waves and human laughter, 90 minutes of music drawn from cultures across our history, and a map built from the positions of pulsars, showing exactly where in the galaxy all of it came from. Carl Sagan, who helped assemble it, described it as a message in a bottle cast into the cosmic ocean. Long after this spacecraft's last transmission ever reaches Earth, long after everyone currently working on this mission has lived out their own lives, that record keeps moving through the dark, carrying, in whatever form the physics allows, the simple fact that a species once existed here that wondered enough about what was out there to build something and send it beyond everything it had ever known. It's worth being honest about exactly what "can't fully explain" means in the context of everything Voyager 1 has found, since precision matters more than dramatic framing. Nothing about these findings suggests anything supernatural, or anything that breaks known physics. What they genuinely represent is a set of specific, well-documented observations, confirmed by NASA's own instruments and described plainly by NASA's own scientists, that simply don't yet fit cleanly within the models built to predict them beforehand. A persistent hum in interstellar plasma, with two possible competing explanations, a boundary temperature that sounds contradictory until you understand the underlying physics of sparse, low-density gas, a magnetic field that turned out to be connected to the wider galaxy in ways nobody expected. These are exactly the kinds of gaps that drive real, ongoing scientific research, genuine, openly acknowledged holes in our understanding of the region separating our solar system from everything beyond it. Holes that only became visible once a working instrument was finally, physically present to measure them directly, rather than inferred from models built entirely from the safety of a planet still tucked inside the solar system's own protective bubble. There's something worth sitting with in the fact that all of this, the historic planetary flybys, the accidental final photograph of an entire civilization reduced to a single pixel of light, the crossing into interstellar space, the persistent unexplained hum, the near-fatal chip failure and its against-the-odds repair, and now, in 2026, a careful, patient fight to buy a few more months of operation from a power supply that cannot be refueled, all came from a machine that predates the personal computer, running on hardware that would be considered primitive by nearly any modern standard, transmitting information across a gap so vast that light itself takes the better part of a day to cross it. Voyager 1 wasn't built with any of this in mind. Its original mission ended, on paper, in the early 1980s, decades before it ever reached the boundary where its most significant scientific findings were eventually made. And yet, because it kept working, because it kept surviving one aging component failure after another, it managed to hand humanity a genuine historic first. Proof, gathered directly rather than merely calculated, of what actually lies beyond the edge of everything we've ever called home. That story is still unfolding right now as Voyager 1 continues its outward journey, its remaining instruments slowly, one by one, being switched off to conserve a power supply that cannot be replenished, its team at JPL working carefully, patiently, through an experimental repair attempt that might buy the mission a little more time to keep listening to whatever else that persistent, unexplained interstellar hum still has left to tell us. Whether scientists finally determine what that signal actually represents before Voyager 1's last instrument goes silent for good, sometime in the early 2030s, according to current projections, remains an open question. Nobody, not the engineers, not the physicists studying the data, not NASA itself, can currently promise an answer to. 49 years after a rocket lifted off from a launch pad in Florida, carrying a spacecraft nobody expected to matter much beyond a 5-year mission to 2 planets, that same spacecraft is still out there, farther from home than anything else humanity has ever built. Still transmitting, still teaching us things about the universe we didn't know to ask, right up until the exact moment it finally can't anymore. If you want to follow how this story continues, whether the upcoming repair attempt succeeds, whether Voyager 1 makes it to that one light day milestone in November, still fully operational, and what its remaining instruments continue to reveal about the edge of everything, that story is still being actively written right now, 15 billion miles from where you're sitting. Subscribe if you'd like to keep following where it goes.